introductory level clinic on model railroad animation using Arduino microprocessors. So what is it all about? You will learn how to add controlled movement, lighting, and sound to your model railroad easily by using extremely inexpensive and simple computers called Arduinos. Well, like what? Let's start with something simple. We will learn how to turn a light-emitting diode, or LED, on and off under the control of an Arduino microprocessor. We will learn how to add a yellow LED to the top of a tow truck. If we can flash one light, then perhaps we can flash two in synchronization. And maybe we can take a half dozen and make them flicker randomly in a dumpster fire. And then let's take a loop of track and add a sensor and a liquid crystal display to create a speedometer. Next, let's learn about another type of LED and a more lifelike way to control lighting for building interiors. Or add sparkles and sound to a water feature. Or make a larger fire. What do you do before you chop up a pine tree? You have to chop it down. And we will learn how to swing an axe, fell a tree, and enjoy the sound it makes. Finally, we will turn back our clocks to the first time we ever rode a carousel. We will go round and round to the music of random Sousa marches, and then let others ride when our turn is over. Before we go any further, if you write down anything in the clinic, this should be it. http://dackm.github.io github.io. This is my website where absolutely everything in this clinic is documented. There are copies of the videos you just saw and chapters which explain the underlying theory. Not into theory? You can go right to the projects, which contain the detailed instructions on how to create the animations we have just seen. Arduinos control the animations through programs, or sketches as they are called in Arduino speak, and I have included the actual code I used to make the animations you just saw, all for free, no programming required. Even a handout you can print with all the main parts of this clinic summarized. I am using this clinic toward my Author Achievement Program certificate, so I am trying to do a really good and complete job. Now that you know what this clinic is all about, it is time for what us engineers call the speeds and feeds. Arduinos are what we call open source, which means that the design is not patented. Many companies can and do build clones of the original design. Clones are generally less expensive, and I use them exclusively. Arduinos were originally designed in Italy about 2003 to teach youngsters how to program. In this clinic, I will teach you how to use programs, but not how to write them. Arduinos come in many form factors, but they all do about the same thing. This is the Arduino Uno model, and is probably the most commonly used by hobbyists. I don't like it. This is an Arduino Mega. It has about 2.5 more connection points than an Arduino Uno. I have one, but I have never used it. This is an Arduino Nano, and all my new projects use it. Why? Well, it is less expensive than an Uno and does everything that I need in model railroading. I don't like the Uno and Mega because when I wire in external components like LEDs, I must jam a wire into a socket and the connection is never truly secure. When I buy a Nano, I buy ones from a manufacturer called LabFin because they have pins already soldered to the board. You can buy less expensive ones and solder these pins, called headers, yourself, but it is a frustrating task that I find not worth the savings. As an accessory to the LabFin Nano, I also buy an expansion board, and I can plug a Nano right in. I can also insert components into the expansion board sockets and then tighten the screws for a nice secure joint. It is also the least expensive option. What's not to love? I buy over 95% of all my electronic components from Amazon. You can occasionally find Arduino components at trade shows, but unless they offer some especially unique item, I usually buy from Amazon. Chapter 3 of my website lists all of the components I commonly use, their price as of this writing, and their Amazon Standard Identification Number, or ASIN. If you enter the ASIN in Amazon's search bar, then enter a carriage return, their website will find the item for you. But be aware, many electronic components turn over quickly, and a part that is available 1 month may be unavailable the next month. If this happens to you, try to search by descriptive terms and make an intelligent substitution. So, how do we begin? An Arduino can do very little right out of the box. It first needs to be connected to a personal computer by the USB cable that comes with it. So let's plug it in. This gives power to the Arduino, and a small LED in the middle of the chip starts to flash, while the LED next to it remains lit. But to make an Arduino do what we want it to do, we have to download a sketch to it, and this requires us to download and use the Interactive Development Environment, or IDE. The IDE is an application similar to a word processor. In it, we can write sketches of our own or download sketches others write and share with us. The IDE runs under Windows, Macintosh, and Linux computers, but I have experience only with Windows. So how do we get the IDE? We visit the Arduino website at http://arduino.cc/en/main/software. Now let's scroll down about a page worth until we see Download the Arduino IDE. On the right are various systems on which the software can run, and I'll click on the version for Windows 10. The next page gives us the opportunity to contribute to the development of the IDE, and I'll click on Just Download. This website uses the Microsoft Store to distribute the software, and if you are not registered or logged in, you will need to do so. But I am already logged in, so I'll click on the Get button. It's pretty large, so the download takes a while. Now I'll click on the Install button. I'm not going to launch the IDE right away because I want an icon on my desktop for future use. I click on the Windows icon in the lower left and then drag and drop the Arduino entry onto my desktop. I can now double-click on my Arduino icon anytime I want to launch the IDE. Now we are finally ready to animate something. I bought a box of 500 color LEDs manufactured by Daikuna, so let's make a yellow one blink. I first take a 10-inch piece of red wire and solder it to the long lead of the LED. I take a similar piece of black wire and solder it to the short end of the LED and paint the joints with liquid electrical tape and let it dry for about an hour. But before we go any further, let's do a thought experiment. What would happen if you plugged a household lamp that normally runs on 120 volts into a clothes dryer socket which supplies 220 volts? There would probably be a loud bang and some smoke, and the lamp would be fried. The same thing goes for LEDs and Arduinos. My red LED runs on 2 volts, but the pins on an Arduino supply 5 volts. I won't go into the electrical engineering here. If you want the theory, read Chapter 4 on my Amazing Arduino Animations website. But to keep my LED from burning up, I need to add a 150 ohm or larger resistor into the line. Although I can add the resistor to either wire, I am going to splice it into the black wire, about 2 inches from the free end. After soldering, I'll insulate it with heat shrink wrap. Different LEDs need different size resistors. If you use too small of a resistor, the LED will blow. Too large of a resistor and the LED will get dimmer. I generally use 150 to 220 ohm resistors for 2 volt LEDs, 90 to 220 ohm resistors on 3 volt LEDs, and 10 to 220 ohm resistors on 5 volt LEDs. So when you buy your LEDs, buy some resistors as well. 150 to 220 ohms is a good compromise. I stripped off about 1/4 inch of insulation from the free ends of the wires and tinned the ends. Unplug the Arduino from the USB cable. I always unplug the Arduino when making electrical connections. If you haven't inserted the Arduino Nano into the expansion board yet, do so now, making sure that it is oriented the right way. The USB connector should be near the D12 pin. Raise the screw on pin D2 of the expansion board and insert the red wire and tighten the screw. If the wire doesn't want to go in, take the pointy end of some decal scissors or some other small object and place it in the socket and raise the flap on the inside. Now insert the black end into the socket labeled GND. This is the electrical ground. This completes all the required electrical connections, so we can plug the USB cable back into the Arduino. Now we need to download a sketch into the Arduino, and I have one prepared for just this project. Launch the IDE application and click on File and then New. An almost blank sketch will appear with just the setup and loop functions. Highlight the entire area and hit the delete key because we won't need any of it. I am not going to teach you how to code, but I am going to teach you how to take sketches from my website and load them into the IDE. So open the website at http://dackm.github.io, and down under the Chapter 4 heading labeled "To view a small program to test blinking a single LED, click here." So click there. A new window will open. Highlight the 13 lines of code and do a Control-C to copy the code to the Windows clipboard. Now go back to the Arduino IDE and do a Control-V to paste the code in the area which formerly contained the code from a brand new sketch. This technique of starting a new sketch, deleting the code from the new sketch, going to the website, copying an existing sketch, and then pasting it into the IDE code area is something you will do for all the projects we will describe today. But we are not quite ready to run the sketch. Remember that there are many form factors for an Arduino? Well, the IDE needs to know which one we are using. So we click on Tools, and then on the Boards entry, and scroll down to the Arduino Nano entry and click on it. We also have to configure the port. Again, we click on Tools, then Port. There will probably be only one entry, and it will probably be already selected. But if not, select the one which is highlighted. We are now ready to run the sketch. In the upper left of the IDE is an icon with a dark green arrow on a teal-colored circle. This is the icon that downloads the sketch from your PC to the Arduino. So let's click on it. Down at the bottom of the IDE, it will indicate that the sketch is compiling, then uploading to the Arduino. In a few seconds, the LED will begin to blink. But this is just the beginning. If desired, we could change the sketch. Remember that the IDE is kind of like a word processor? And alter the number of milliseconds that the light is on or off. Changing the on time to 100 milliseconds and the off time to 1900 milliseconds would turn it into more of a strobe. And now you know the basics of animation using Arduinos. Moderators, could we take a break here to see if there are any questions? I'm going to
Okay, I just paused the video right here, and generally if there are any questions, this is where they pop up. We've covered a lot of material real quickly here. Moderators, do you see anything on the feed which we might address right now? Well, I'm a computer scientist by training. So for me, coding is a lot easier than the electrical engineering part of it. So that's why I put it all out there on the website. And every project that you see here today is out there on the website. All you've got to do is copy and paste. So let's continue on.
pick up the pace just a bit. The tow truck I used is one from the Scene Master series from Walthers. There is a small screw on the underside, and if I remove it, detaches the cab and steps from the frame. I took the cab to my drill press and carefully drilled a number 55 pilot hole through the top of the cab from the outside. I also drilled one through the interior. I then enlarged the holes with the number 29 bit. If you don't have a set of numbered drill bits, use a 1/8 inch bit. If you don't have a drill press, use a cordless drill and hold the workpiece gently in a vise or clamp. Now from the inside, I inserted the LED into the hole in the roof and attached it with a bit of CA glue. I ran wires through the interior, then reattached the cab to the frame. But how do we power these things when on the layout? We can't always have them connected to our PC for power. That's where wall warts and barrier strips come in. Wall warts are the things that plug into the wall to power audio components and other electronic devices, and we need one that can provide somewhere between 7 and 12 volts DC and at least 250 milliamps. You may have one lying around from some obsolete device, but if not, you can buy one from Amazon for about $5. You can buy ones with more capacity, I do, which allow you to power more than one Arduino or power external devices which can be controlled by an Arduino. I usually cut off the end of the power supply, peel back several inches from the outside insulation, and use a voltmeter to make sure I know which wire is hot and which wire is the ground. I solder spade connectors to the wire ends and connect it to a screw-type barrier strip. I then use red and black 20-gauge wires to run from the barrier strip to the VIN voltage input and GND wires of the expansion board. Using the barrier strip makes it easy to get to a ground point when wiring in additional LEDs or other components, so don't skip that step. Barrier strips come with various numbers of connecting points, and I always buy long ones and then cut them down with a bandsaw. Amazon is expensive for these things, so if you have an electronic supply store locally, you may want to shop there. Okay, let's try something new. I've prepared two more LEDs, a red one and a blue one, and connected their red wires into pins D7 and D8, and their black wires to the ground point on the barrier strip. I always solder a spade connector on any wire to be placed on a barrier strip, but it's your choice. I also went back to the website and downloaded another sketch from underneath the Chapter 4 heading, the one labeled, "To view a small program and test blinking a pair of LEDs, click here." We now have 3 LEDs on the same Arduino, but this new sketch will power only the 2 new ones. When we run this sketch, the red and the blue LEDs blink alternately every second. Using the same method as we used for the tow truck, we can install these into a police car. Next comes the dumpster fire, and you are probably getting the hang of things now. I prepared 4 yellow and 2 red LEDs for this project. I now need to tell you that 6 digital pins on an Arduino, numbers 3, 5, 6, 9, 10, and 11, have special powers called pulse width modulation, or PWM for short, which means that they can be made to dim through software, can appear to get dimmer and brighter every few hundredths of a second, which can yield a flickering effect great for simulating fires. Just prepare your LEDs as before, and remember, even though we are dimming the LEDs through coding, they still need a resistor. I drilled some holes in a dumpster and ran the wires through the holes. I didn't want to solder spade connectors to 6 ground wires, so instead I bundled 3 together at a time and soldered a pigtail to the bundle, insulating the joint with heat shrink tubing, and soldered a spade connector to the free end of the pigtail. I connected the spade connectors to the ground position of the barrier strip. You did use black colored wire for your LED ground wires, didn't you? And then connected the red LED wires into the expansion board positions listed above. The LEDs tended to wiggle around in the dumpster, so I secured them with clear silicone caulk. Don't worry about getting any on top of the LEDs, because doing so tends to diffuse their light, and I like the effect. I added some small pieces of balsa wood inside the dumpster, and you can add tires, pallets, or other junk as desired. The code for the dumpster fire can be found under Project 1. The code in the loop function sets the flicker level for each pin to some value between 50 and 255, 255 being full power, and then resets every power level every 1/10 of a second. 255 is pretty bright, so you might want to play around with the minimum and maximum values I provided. Now for the speedometer, the first project I ever created. No LEDs used here, but we are going to use a light-dependent resistor, also known as an LDR or photocell, and a 4-line liquid crystal display, a 4-position barrier strip, and a 10K resistor. I'm not going into as great detail for the remainder of the projects, as you can find all you need in the documentation in the website. For starters, I took the LDR and soldered 24 inches of lightweight wires onto the 2 leads and insulated the joints. An LDR is symmetrical, so when hooking it up, one lead is the same as the other. You can use any size or color wire here, just not black, red, or white. I drilled a hole through the track and through my layout large enough so that I could place the LDR even with the track ties. You might even need to remove a tie to make this work. Positions 1 and 2 of the barrier strip are used for the wall wart to provide power to the Arduino. So now is the time to run red and black wires from the barrier strip to the VIN and ground positions of the expansion board. Use masking tape and label the 3rd position of the barrier strip as 5V and the 4th position as A0. Connect one lead from the LDR to A0 and the other to 5V. Take the 10K resistor and wire one end to the ground position of the barrier strip and the other end to the A0 position. Run another wire from the A0 position of the barrier strip to the A0 pin on the expansion board. We should now have 3 wires connected to the A0 position of the barrier strip. Run another wire from 5V on the barrier strip to the 5V position on the expansion board. Now for the liquid crystal display. Run a black wire from the ground position of the barrier strip to the GND position of the display. Note that the display has male connectors, so female jumper wires are needed to mate with it. Run a white or red wire from the 5V position of the barrier strip to the VCC position of the display. Run any color wire from A4 on the expansion board to SDA on the display. Run another wire of any color from A5 on the expansion board to SCL on the display. Our wiring is now complete. Once you apply power, you may need to turn the blue potentiometer on the back of the display to adjust the contrast. Visit the website and copy the code from Project 2 Speedometer section and paste it into the code section of a blank project. But before you run the code, you need to make two changes. Around line 179, you need to change the code to represent the length of your track loop in inches. Around line 180, you need to record your track scale. Save your changes by clicking on File, then Save, giving the project a file name of your choice. As they say in Indianapolis, ladies and gentlemen, start your engines. When your locomotive passes over the LDR, the Arduino will start its timer. When it passes over the LDR again, it will report the elapsed time and average scale speed on the display and starts the cycle over again. You can run the locomotive standalone or with cars. I was surprised just how much faster the train ran after it was a bit warmed up. I like this approach for a speedometer on a loop rather than a speedometer on a stick because it handles momentum better, uses only a single sensor, and probably is a little bit more precise. The current version, 0.54, does have a small bug which can pop up when running with short cars, and I am working on a bug fix.
Just a comment here. I mentioned that version 54 has a bug. Well, the current version that's out on the website is version 55, where that bug has been corrected.
The next project, the lighted building, uses a different way to control the lighting. I used 5-volt LEDs for this project, running at 40 milliamps, more powerful than LEDs we have used before. These LEDs come on rolls, so you just need to use scissors and snip one off. The front of the unit is curved and tends to roll when soldering, so I place the unit curved side down and place a piece of masking tape on it to hold it steady. With the back side up, I pull back a bit of the backing tape. The front of the LED indicated which of the soldered pads was for the ground and which was for power. I dropped a bit of solder on each dot and tinned the ends of a black and a white 28-gauge wire, and then made the soldered connections. I removed the LEDs from my work surface and placed a spot of masking tape over the actual LED. I then spray painted about 2 inches of the wire around the LED so that the black wire would be less visible when the unit was attached to the ceilings. I made the building interior using 3D printing, but that's a topic for another clinic. You can build room pods with sheet styrene or some other technique of your choice. I decided what business was to be in each room and found images on the web to represent the motorcycle shop on the bottom floor, the bowling alley and utility room on the middle floor, and the bar and the ballroom on the top floor. I glued the images on the building with rubber cement. Drilling from the inside, I drilled 1/8-inch holes at the center top of each room and passed the wiring through the hole. I removed the backing from the LED and pressed it onto each room's ceiling. But how do these lights go on and off at random? I am not going into the details, but if you look at lines 86 through 92, you can see the parameters for what I call a light block. Line 86 says that for light block number 1, the positive wire of the LED goes to pin D7 of the Arduino. Line 87 says that when the Arduino passes the initial power up test, this particular LED is off. Lines 88 and 89 say that the minimum on time is 8,000 milliseconds, or 8 seconds, and the maximum on time is also 8 seconds. These values are usually different from each other, and the actual time on is some random value between the minimum and maximum. But for this room, I wanted them to be the same. Lines 90 and 91 give the minimum and maximum values for the off time. Line 92 gives the elapsed time when the state of the LED will next change. There are blocks for up to 9 LEDs, and the code is written to cause them each to change as desired. Additionally, line 84 specifies how many of the blocks are actually used in any particular application. So, upload the code to the Arduino, cover the interior with the building shell, and enjoy. I used basically the same code for a waterfall. I used regular 3mm LEDs for this project, so with their smaller current draw, I could use a bunch. I prepared the waterfall with Woodland Scenic Shaper Sheet and then covered it with plaster. I made the first pour with Cast & Craft polyester resin from Michaels, about 3 ounces, tinted with a small amount of Pearlex Sapphire solid pigment. I let the resin sit for about 15 minutes until it was as thick as syrup, and then tilted the structure and made the first pour all at once. Within a minute, it was no longer runny. I pressed in a few rocks and twigs and let it harden overnight. The next day, I drilled 9 1/8-inch holes into the feature. I prepared 3 blue 3mm LEDs from Daikuna, 3 white ones, and 3 additional white LEDs, 1 each tinted with Woodland Scenic's navy blue, turquoise, and 1 Tamiya clear blue. I placed the LEDs in the holes and sealed them in place with clear silicone caulk. I let them dry overnight. The following day, I made another resin pour of about 2 ounces, this time with clear resin, and let it dry overnight. Finally, I gave the whole thing a coat of dull coat. Oh, and I added sound. The sound chip and amplifier each require 5 volts, and the power supply provides 12 volts, so I had a problem. I could run it from the 5-volt pin of the Arduino, but I was afraid too much power would be consumed, so downstream of the power supply's barrier strip, I wired in a buck converter, or voltage regulator I purchased from Amazon. Downstream of the buck converter, I wired in another barrier strip. But before I wired in the MP3 player and the amplifier, I dialed down the converter to 4.2 volts because the web said it ran better at this lower voltage. This must be done before attaching the MP3 player and amp, because out of the box, the converter delivers 35 volts, and we don't want to fry the audio components. The MP3 player and amplifier are just chips, with no convenient way to mount them to a fascia board, but I found a solution. The space between the pins of the Arduino is 1/10 of an inch, or probably something close to that in metric units. This same spacing is used between the pins of the MP3 player and the amplifier, probably some industry standard. Perhaps we could re-engineer the Arduino expansion board to fit these 2 audio chips, and that's what I did. I cut the expansion board lengthwise on my band saw. Because the expansion board has 15 pins on a side, and the MP3 player has only 8, I cut one piece of the expansion board crosswise at pin 9. With the sacrifice of pin 9, that left me with 2 pieces, one with 8 pins and one with 6. But while we need pins 1 through 8 on one side of the MP3 player, we really only need 1 pin on the other side, pin 16. And we don't even need pin 16 for every project. Unfortunately, the distance between the 2 rows of pins was not the same between the Arduino and the MP3 player, so I took a thick piece of sheet styrene, placed the MP3 player into the 2 expansion board pieces, and hot glued the pieces to the styrene. Bingo! I invented a way to make an expansion board for the MP3 player and the amp. I have used a bandsaw for years, but using large saws can be dangerous. If you don't feel comfortable with making these cuts, ask someone with more experience for help. Safety first. Once the MP3 player and amp have their power connections, I ran wires from pins 7 and 8 of the Arduino to the MP3 player, pins from the MP3 player to the amp, and from the amp to a speaker. Chapter 9 has all the details on the wiring. Because the MP3 player has its own built-in amplifier, you can get by without a separate amplifier. The MP3 player can be wired up directly to the speaker by using different pins. But then there is no way to dial the volume up or down except through software. There is a micro SD card in the MP3 player, on which I placed an MP3 file of falling water I downloaded from the internet. Actually, it was part of a relaxation video, and I stripped out just the audio. No need for stereo, so I removed the second track using the free audio editing software from Audacity. I connected up a wall wart and barrier strip and plugged it in. Lights, sound, action will come next. I know somebody watching today has to have visited the magnificent HO layout in the Chicago Museum of Science and Industry. Did you see the falling tree back where they modeled the area around Seattle? I had to have a falling tree. This is the first project where I used motors. Arduinos can drive small stepper and servo motors directly without a separate motor shield. I used servos because they are absolute in positioning. They always know where 0 degrees is. Steppers are relative. I wanted the tree and the lumberjack to always know their starting position. Like the Waterfall, this project is going to use audio, so like before, I wired in a buck converter, barrier strip, MP3 player, amplifier, and speaker. The motors for the lumberjack and the tree both require between 4.2 and 5 volts, as well as ground. And fortunately, we have that coming out of the buck converter. To control the lumberjack, I ran a wire from pin 2 of the expansion board to the control wire of the servo. The other 2 wires, red and black, are for power and ground and should be connected to the output of the buck converter. A wire from pin 4 should be connected to the wire controlling the motor, which controls the tree. I also wired in a display and push button to start the animation. The wiring for the display is similar to what we used on the Speedometer project, and wiring a push-button switch is described in Chapter 8. The mechanicals are the most difficult part of this project. How do we mount the tree to the motor and the motor to the layout? How do we connect the lumberjack to his motor and make him turn? There is just not enough time to go into these specifics today, but that's where the website can help. If you want to see the details, go to the heading for Project 4 Lumberjack and open the videos there. For now, know that I purchased the figure over the internet at modeltechstudios.com, but lots of options exist for this. I created simple mounting blocks out of lumber and attached them to the servo. The servo for the tree is mounted horizontally, and the servo for the figure is mounted vertically, and I glued them with Titebond 2 glue. I used epoxy and Teflon plumber's tape to attach the tree to the motor's arm. I made a platform and axle to hold the figure and took evergreen tubing to construct a transmission. Placing the lumberjack accurately is not as tough as it may seem once you know the trick. If I were to do this project again, I would visit my hobby shop and ask for advice on servos. The low-cost ones I bought were problematic. Originally, the metal-geared one I used to rotate the lumberjack was very noisy, so I replaced it with one using plastic gears. I really disliked the open slot for the tree, but the motor manufacturer did not offer a right-angle horn that might be used to hold a door that would rotate out of the way when the tree began to fall. Better servos, like are used in radio-controlled cars and planes, might have better options for horns. Or perhaps I need to make some of my own using 3D printing. Finally, we have the Carousel. The Carousel is an old IHC kit which can still be found on eBay or at swap meets. The overall design is similar to the Lumberjack in that it has audio circuitry and a display. It uses a toggle switch instead of a push button, but the switch wiring is quite similar. It uses a single 12-volt Hankscraft motor to drive the Carousel, but requires a second buck converter to drop the voltage to where the carousel is spinning at a safe speed. I added a wire from pin 16 of the MP3 player to pin 9 of the Arduino. Although not needed for earlier projects, this wire tells the Arduino when a song is finished. When a song completed, I used a relay controlled by the Arduino to stop the carousel's motor. I found carousel music on the web by searching for Sousa marches and downloading the MP3 files by right-clicking on their progress bar and saving them to the SD card. I found 14 of them that I liked. However many you choose, when you download the code, change line 23 to indicate the number of songs you place on the chip. The trick to this project is mounting the carousel and Hankscraft motor successfully. And again, the mechanicals can be found at the website. Without going into the details, I drilled a 1 3/4 inch hole in the layout. I made a mounting block out of lumber and drilled a 1 3/4 hole for the motor in it. I aligned the hole in the layout with the hole in the mounting block, clamped them, and drilled 4 holes for machine screws, aka bolts. The mounting block is separated from the layout bottom using spacers. After I clumsily broke off the plastic axle on the carousel, I used a 1/8 inch steel rod to replace it. I connected the new carousel axle and the Hankscraft motor with a coupler I found on Amazon and secured it to the motor and carousel rod with the set screws on the coupler. Well, folks, that's about it for amazing Arduino animations for 2020. If you have any questions or find any areas where things could be improved, just drop me a line at acmans@charter.net. Don't forget, YouTube is an amazing source of tutorials on all things Arduino and model railroading. I hope you enjoyed the ride. Time for more questions. Thanks for tuning in to this